Hi guys, my name is Jamie Leidy and I'm going to be doing my breakdown of glucose in this presentation. So we're going to start with step 1 in the next slide. In the first step of glycolysis, the glucose ring is phosphorylated. Phosphorylation is a process of adding a phosphate group to a molecule derived from ATP. As a result, at this point in glycolysis, one molecule of ATP has been consumed. Enzymes that catalyze the phosphorylation of the many six-membered glucose-like ring structures. A kinase is the name given to an enzyme that phosphorylates other molecules. Atomic magnesium is also involved to help shield the negative charges from the phosphate groups of the ATP molecule. This result of this phosphorylation is a molecule called the glucose 6-phosphate, thusly called because the 6 carbons of the glucose acquires the phosphate group. Now, in the second step of glycolysis, it involves the conversion of a glucose 6-phosphate to a fructose 6-phosphate. This reaction occurs with the help of the enzymes phosphoglucosamidase. As the name of the enzyme suggests, this reaction involves an isomerization reaction. The reaction involves the rearrangement of the carbon-oxygen bond to transform the 6-membered ring into a 5-membered ring. To rearrange takes place when the 6-membered ring opens and then closes in such a way that the first carbon becomes a new external to the ring. In the third step of glycolysis, the fructose 6-phosphate is then converted to a fructose 1,6-biphosphate. Similar to the reaction that occurs in step 1 of glycolysis, a second molecule of ATP provides a phosphate group that is added to the F6P molecule. Now then the enzymes will catalyze, and this reaction is a phosphofructase kinase. As in step 1, a magnesium atom is involved to help shield the negative charges. Now for step 4, it's the final step of the glycolysis which utilizes the enzyme ATAlase, which catalyzes the cleavage of the FBP to yield 2 3-carbon molecules. One of these molecules is called the glyceride 3-phosphate, and the GAP is the only molecule that continues the glycolytic pathways. As a result, all of the DHAP molecules produced are further acted on by the enzymes triphosphates amylase, which organizes the DHAP into GAP so it can continue into glycolysis. At this point in the glycolytic pathway, we have 2 3-carbon molecules, but have not yet fully converted glucose into pyruvate. Next, we will have step 5. Now, in step 5, the two main events that take place are the glyceride 3-phosphate is oxidized by the coenzyme nicomyde adenine dinucleotide. The second molecule, phosphorylated by the addition of a free phosphate group that catalyzes this reaction, is the glyceride 3-phosphate. The chemistry that takes place in this reaction is more complex than that of the previous reaction we've discussed. The knowledge of organic chemistry is needed to understand the specific mechanisms of the conversion. Generally, the enzyme GHAPDH contains appropriate structures and holds the molecule in conformation such that it allows the NAD molecule to pull hydrogen off the GAP, converting the NAD to NADH. The phosphate group then attacks the GAP molecule and releases it from the enzymes to yield 1,3-biphosphate, NADH, and hydrogen atom. We will come back to this role of this NAD-NADH molecule in the next step. Now in step 6, 1 and 3-biphosphate is converted into 3-phosphocyanurate by the enzyme phosphoglycerate kinase. This reaction involves the loss of a phosphate group from the starting material. The phosphate is transformed into a molecule of ADP that yields our first molecule of ATP. Since we actually have 2 molecules of 1,3-phosphoglycerate, we actually synthesize 2 molecules of ATP in this step. With the synthesis of ATP, we have canceled the first two molecules of ATP that we used, leaving us with a net of 0 ATP molecules up to this stage of the glycolysis. Again, we see an atom of magnesium is involved to shield the negative charges on the phosphate groups of the ATP molecule. Now we enter step 7. This step involves a rearrangement of the position of the phosphate groups on the 3-phosphoglycerate molecule, making it a 2-phosphoglycerate. The molecule responsible for catalyzing this reaction is called the phosphoglycerate mutase. A mutase is an enzyme that catalyzes the transfer of a functional group from one position of a molecule to another. The reaction mechanism proceeds by first adding an additional phosphate group to the second position of the 3-phosphoglycerate. The enzymes then remove the phosphate group from the 3 position, leaving it just the 2-phosphate, and thus yielding 2-phosphoglycerates. In this way, the enzyme is also restored to its original phosphorylated state. Now we have step 8, which involves the conversion of 2-phosphoglycerates to phosphoenolopyruvate. The reaction catalyzed by the enzyme enolase. Enolase works by removing a water group or dehydrating the 2-phosphoglycerates. Now we come to step 9. The final step of glycolysis converts the phospholurate into pyruvate, which then helps the enzyme pyruvate kinase. As the enzyme's name suggests, this reaction involves the transfer of a phosphate group. The phosphate group attached to the 2-carbon of the PEP is transferred to a molecule of ADP, yielding an ATP. Again, since there are 2 molecules of PEP, here we actually generate 2 molecules of ATP. We have now completed the steps of glycolysis. If we go back and count our ATP usage and generation, we find that we have consumed 2 molecules of ATP and generated 4 to leave a net gain of 2 ATP molecules from the glycolytic pathway. We have gone from our starting product of glucose to our final product, pyruvate. Here in this slide, you can see the full step of the glycolysis process all at one time, not broken down. Now, when you look at this step and you wonder how does it affect in a high intensity when it comes to ATP, you'll notice that with a higher intensity, you're going to be yielding more ATPs than you normally would.